Hello, we are Group 2, and welcome to our presentation on our case study, which is Renewable Energy Grid Management.
I'm Kevin, and this is our team. First is me, Kevin Pradipta. Second is Courageux Yekti, or Jesse. Third, we have Azrael, Mika, Palito Tobing. And fourth, Akrom, Karuma, Ferdian. Introduction. Renewable energy is being integrated into power grids, but its unpredictability due to weather causes supply-demand imbalance. Now, however, non-renewable energy sources, while reliable, have environmental drawbacks. Efficient grid. To make an efficient grid management, solutions are needed to balance renewable and non-renewable energy uses. Now, the problems are traditional energy methods rely heavily on weather conditions. So if the weather is bad, we can't really do anything because there's an imbalance. And the use of traditional renewable energy often leads to imbalance between supply and demand, and a storage solution is needed to accommodate excess energy produced because we can make more energy because of the good weather. And finally, we need to minimize or reduce the reliance on non-renewable energy. Now, the goals are balancing energy supply and demand based on weather condition is essential for grid stability. Next, ensure efficient and effective energy storage to optimize grid performance. Third, we have develop a system to predict weather conditions and adjust energy strategies if the weather deviates from forecasts. Fourth, maximize reliance on renewable energy while minimizing or eliminating the use of non-renewable energy. Now, the balancing energy supply and demand based on weather, that means if the demand is high but the weather is bad, we might have to drop the supply and the demand must be lowered. And ensure efficient and effective energy storage so we can access, let's say we have more than supply and the demand is low and the supply is high, we need to store it. That way, if we have a bad weather and our supply is low, we can use the stored energy instead of relying on the non-renewable energy. And develop a system to predict the weather. That way we can predict and how much to use the battery instead of waiting. If we wait, then the power is gonna shut down for a bit, so it's gonna be bad. And fourth, we need to maximize reliance on non-renewable energy instead of non-renewable energy, because the whole thing is we have to rely on renewable energy and remove the non-renewable energy so we can fix the environmental issues.
Okay, hello everyone. Now my name is Azrael Mika Palito Tobing, and my MPN number is 240644822. And now I'm gonna presentate my study case 3 from Group 2 in computational thinking 5. Okay, now this is the key variables. There are the weather conditions like temperature, wind speed, and sunlight. Also affects renewable energy generation of solar and wind. Also there is energy generations that are renewable sources, solar, wind. Also non-renewable sources like coal and gas. There are also an energy demand, that is consumer demand varies throughout the day, peak hours of peak hours. Also there is energy storage, that is battery capacity to store excess energy, and also used during too low generations of periods. And the last thing is the grid stability, that is the frequency and voltage must be maintained and critical for preventing blackouts. Okay, for the next one, there is the challenges that is unpredictably to the renewable energy, that are solar and wind energy, depend on weather conditions, which are highly variable. It is hard to predict an exact energy generations. Balancing supply and demand must ensure energy supplies meets demand in real time. Also, the excess energy must be stored or diverted, while the effects require backup from non-renewable sources. Also for the grid stability, there are fluctuations and in energy supply can destabilize the grid. Also, it could require real-time adjustments to maintain stability. For the last thing is the cost efficiency, which is minimizing the reliance on non-renewable energy to reduce cost and environmental impact. There are also balancing costs with the need for reliable energy supply. So I'm going to discuss also the patterns identified. It is whether the driven energy generations, the solar energy, high during sunny weather, low during cloudy weather, and zero at night. Also there is a wind energy that is high during windy winter, low during calm conditions. Next thing is the demand fluctuations. That is energy demand varies throughout the day or peak during mornings and evenings and lower at night. There's also energy storage usage. That's excess energy stored in batteries during periods of high generation and low demand. There's also stored energy that is used during periods of low generation and high demand. Also, lastly, there are the non-renewable energy as backup, which is non-renewable energy is used only when renewable energy and stored energy are insufficient to meet the demand. That's all from me, Azarul Palito Tobing, and I'm from Metallurgy and Material Engineering, Metallurgical and Material Engineering, and thank you for listening.
Hello, it's Jesse speaking again here. So as you can see here, we have our data abstraction, and it does relate to the patterns that we have recognized here. So if it's sunnier, we'll have a higher solar energy, and if it's less sunny, we'll have a lesser solar energy. And if it's more windy, we'll have a higher wind energy. If it's less windy, we'll have less wind energy. And we can see how much total renewable energy we have from that one, from those two combined, the solar and the wind, and we can see what action we need to take. So to predict how much renewable energy we have based on those factors, we can use this simple algorithm here just to see if it's sunnier, we'll have a higher solar factor. If it's less sunny, like it's only cloudy, we'll only have a solar factor of 0.5. And if it's not sunny at all, we'll have a solar factor of 0. And we just times that by 100 and we'll get the solar energy. So the basic idea is just the less sunny, the less solar factor, the less solar energy. Same with the wind. The windier it is, the higher the wind factor, which means the higher the wind energy. And we can put that function in the main algorithm, which is just basically, if the renewable energy is more than the demand, then we just store the excess energy or divert it, and then we don't need to use any non-renewable energy. Otherwise, we count the deficit, and if the storage is more than the deficit, then all we have to do is use the stored energy, and we don't need to use any non-renewable energy. Otherwise, we have to use the stored energy and the stored energy and the renewable energy and our non-renewable energy. But we have to use all of our renewable energy and all of our storage before we can use our non-renewable energy. So as you can see, it's basically just trying to use the least amount of non-renewable energy possible. And that's the basic goal here. So as you can see here, we have a flowchart of our algorithm, but a little bit simplified. Now basically, it's just the same thing. We just have our input, which is the energy demand, and we have the other input, which is which we'll put into the algorithm to detect how much renewable energy that we have. So then we make a decision from there. If the energy demand is less than the energy received, then we have enough renewable energy, and all we have to do is just use all of that and store the excess energy, and we just go on. And in another case, if this is false, and so which means energy demand is not less than the energy received, but the energy demand is equal to the energy received, and that is true, then all we have to do is just also use the renewable energy and then go on. But if the energy demand is not equal to the energy received, then we have to use the battery as well, and if that's enough, we just go on. But if that's not enough, then we have to use the non-renewable energy. So as you can see from this algorithm, the non-renewable energy is the very last resort that we're going to use, and that's basically the whole idea. We're just trying to use as much renewable energy possible and the least non-renewable energy possible.
And today I'm going to tell you about slides 12 and 15. Okay, let's start off with slide 12. Another example. As you can see, we have time, weather, solar energy, wind energy, total renewable energy, demand, storage, and action taken. For time, we have 7 p.m. For weather, we have dark and windy. Solar energy, we have 0. Wind energy, we have 200. And our total renewable energy, we have 200. Our demand is 300, and our storage is 100. And action taken, use non-renewable energy plus storage energy. Assuming in this different case, we have a storage of 100, we can see what action the algorithm tells us to take. Okay, let's move on to slide 13, our Pico analysis. We have the image right here in our right. The first one is time complexity, or constant time. The algorithm performs a fixed number of operations like comparison arithmetic regardless of input sizes. Space complexity, or constant space. It uses a constant amount of memory like variables for energy, demand, and storage. This is because our algorithm does not contain any loops or recursion and only has a fixed number of operations. Also, the input does not change the number of steps in algorithms. Okay, let's move on to slide 14, the real-world implementation and builder innovations. We have 3 countries in here who has the implementation, and those are Denmark, Germany, and Uruguay. Denmark achieved over 50% of electric generation from wind energy by using grid interconnectivity with neighboring countries' community ownership model for wind turbines. Germany has successfully integration of solar and wind energy by energy wind policy implementation and also investment in smart grid technology and energy storage. Uruguay, rapid transition to wind power, achieving 30% of electricity mix by comprehensive energy plan and political consensus and long-term contract for wind developers. And we have here three of our way to innovation is advanced AI and machine learning application, deep learning for complex pattern recognition in energy system, and reinforcement learning for adaptive grid management strategies. And the second is integration of electric vehicle, or well known as EVs, vehicle to grid or V2G for short, technology for using EVs as distributed energy storage. Lastly, microgrids and decentralized energy system. It has resilience and local energy market and also integration with main grid for optimized energy distribution. And we come to slide 15, and this is the conclusion. For our summary, we have designed a simple and efficient algorithm to optimize energy consumption in a smart grid. The algorithm adjusts energy use based on real-time weather data, demand, and storage levels. It prioritizes renewable energy, uses storage energy when available, and relies on non-renewable energy only as a last resort. Why it works? There are three main reasons on why it works. The first one is it uses weather data to predict renewable energy generation, for example, solar and wind. And the second one is it dynamically balances energy supply and demand in real time. And lastly, it's a simple algorithm, so it runs in constant on one time, making it scalable. The key takeaway here is the algorithm shows us how we can use complex thinking to turn abstract concept into concrete algorithms. And lastly, we have future improvement, and we have two solutions. And we have two. Our current algorithm is a bit simple for real world application, but the general framework and ideas can be expanded to have it consider other variables like future demand equation for demand, etc. And lastly, we can definitely implement more complex formula for the energy consumption and protection and production. From the renewable energy sources, like we could include specific UV levels, time exposure, and etc. using real scientific formulas in the future. But for now, we just use this to demonstrate how we can use an algorithm to solve a problem. That's it for now. Thank you all for listening, and have a great day.